Cool. So welcome to this video, guys. Today we're going to be covering the internet and sockets. So when it comes to the internet, the way you transfer information, transfer data is the internet protocol, right? IP. Now, you don't really need to know how IP works for the exam, I believe, but essentially, as long as you know that data is transferred from one device to another through IP, then you'll be able to understand how everything works within the TCP IP stack. So TCP, which also stands for Transmission Control Protocol, is basically this sort of structure built upon this internet protocol that allows for communication in a structured way. Now it has these four layers, so we'll go through each of them in a bit of detail, and then we'll go into a bit more detail in the next few slides. So first of all, you have the application layer. In this application layer, we handle client-side like sort of things. So let's say you're making a Word document and you're now trying to convert it. That's your application layer. Um, and like when you're trying to prepare these protocols um, from your actual data. So essentially things like determining the structure of packets, things like that. So your protocols like HTTP, FTP, DNS, SMTP protocols so basically anything that involves user services will be on your application layer. Then have your transport layer, or essentially it basically will manage your end-to-end connections. So things like we mentioned TCP. Now TCP, I will be going into a little bit more detail of how TCP works in UDP, but essentially all you need to know for now is that it's a connection-oriented and reliable way of transferring data packets or basically data from one device to another. Now, when I talk about packets, what I mean is that when we send data from one device to another, we can't send like a really massive file over the internet, right? So we split this data into packets, um, in which we have various different things. So you have like um, you'll have in TCP at least, you will have mainly a header containing information about the data within this sort of little packet that's being sent across the internet, and then your data itself. Now, I have a few more slides about this as well, so I'll go into more detail in the next few slides. This is just a more of an intro slide. Um, After the transport layer, when we manage these end-to-end connections, when we use these TCP and UDP um, sort of protocols. We then move on to the internet layer, which is where we do routing, right? So routing is basically just dealing with things like IP addresses. So these are the unique identifiers for devices on the internet. Dealing with ARP. So things like so ARP stands for Address Resolution Protocol. So basically anything to do with sort of routing the data to the correct person um, is going to be dealt with on the internet layer. And for the last one, it's the network interface layer or the link layer. I'll refer to it as the link layer because I believe that is what it's referred to in the slides for security networks. But the link layer is basically the physical transmission of your data. So that's actually like sending your data through everything, um, like your wires and stuff like that. And then also hardware addressing. So managing physical addresses, so like things like MAC addresses, which I'll move on to in a bit more detail in the next few slides, like I say. So yeah, this is the IP packet structure. I have kind of stolen this from the slides, but you can see this is sort of what you would have when you send your sort of packet or packets across. Each packet will look quite similar to this. So, like we said, each packet consists of a structured header and data. So this header is basically everything on the bottom table kind of thing, except for the options. So that is the whole header, and then you have the data after. So the header contains a lot of different information that will help route, fragment, and process packets. So routing, obviously meaning when we're sending this, let's say we're sending a internet message across from like my phone to like someone else's phone in like the US, right? So let's say, obviously we can't send it directly. It will go through various different nodes in order to actually go to where I want it to. So like from like let's say I'm sitting on my house, it will go from my device to my router, and then it might go to like some ISP or internet service provider and its nodes and move through that until it can get to the US, and then it will go from the US to that person's router and then to the the person themselves. Um, when we talk about fragmentation, um, hold up, what did I mean by fragmentation? I feel like I've forgotten it. Oh God. I'll talk about that in a few more slides. I think I do have one. If not, let me just write that down. Fragmentation. Okay, cool. Um, and then obviously processing packets efficiently. So if you actually have a look at the header, right, you have a lot of different things. So for example, we have the 4-bit version. We have a 4-bit header length. We have the 8-bit type of service, so that will obviously tell us how we're actually transferring data on TCP or IP, I mean, or UDP or whatever. Um, you also have the identification, 16 bits of identification. We have flags, which are 3 bits, which we can use to sort of show that some things are on, some things are off, things like that. Um, and we also have time to live. Now, time to live is basically like let's say back to the example of if I'm sending a message on Instagram to my friend in the US. Like obviously that's quite far, and we're gonna have like sort of we're going to have to go through many sort of nodes to actually reach um, this person in the US, right? So this time to live is something that's quite good. It will essentially be like a number, and we decrement this number each time when we go to a node. And so it will prevent us from sort of traversing nodes too much and not being able to find the destination source address or where we want to send it. Um, Also, we have a 16-bit header checksum, which is just some mathematical calculation where um, we are sort of allowed to check if our packets have all arrived and are all in order, and the data hasn't been sort of messed up or anything like that. Um, so yeah. So yeah, this is the whole thing, the TCP IP stack in a bit more detail. Um, So yeah, as you can see, we have the application layer, transport layer. I've also included the TLS layer as well, which is actually between application and transport. Um, so yeah, you can see firstly in the application layer, we format data for user applications. Transport layer, we segment the data into packets. We manage the connections either via TCP or UDP. Now, like I said before, TCP is more of a reliable sort of packet transmission um, sort of protocol. Now, this is because it has things like handshakes. Um, so what will happen is we can send like a synchronization message from a client to a server, and then the server will send a synchronization acknowledgement back to the client, and then the client will acknowledge that synchronization um, acknowledgement as well. This is known as the three-way handshake. So it's basically just a way of saying, okay, I want to connect with you, first of all. Then the server will be like, okay, cool, let's connect. And then the client will just be like, okay, cool, sorted. And then they've at that point they've confirmed that they want to communicate via TCP. Um, and then also you have the sequencing as well. So packets are obviously going to be sent randomly and they're going to arrive at different times depending on what route they take. When we talk about like these nodes, right? So TCP essentially within the header, um, we can have like these packet numbers where these packets will order themselves once they arrive at the destination, um, which is a good thing about TCP. Now, UDP on the other hand is it's connectionless. It's more unreliable, but it's more low latency since your headers don't actually contain as much information as you would have in TCP. So it's really good for like things like, for example, like Discord, where we need fast data transmission um, from my voice to you guys, like through your speakers. Um, and yeah, it's pretty good for that kind of thing. So TLS layer, obviously TLS stands for Transport Layer Security. It will encrypt communication between application and transport layers. And essentially, in a nutshell, since obviously I will have another lecture about this, I'll just go through it in brief detail. Essentially, we, as a client, will send a cipher suite, well, not a cipher suite, but all the different ciphers that we support, and then the server will pick one of them, and then we will perform um, essentially a key sort of transmission or key exchange, sorry, protocol, such as like Diffie-Hellman, in order to get a sort of session key. And then once we have this session key, we can then use it to encrypt information. Um, Now, this TLS layer is only used in HTTPS, I believe. Um, so that's another thing to note. Obviously, HTTP is Hypertext Transfer Protocol. This is like what you usually use if you're accessing stuff on the internet. HTTPS is just the secure version of it where we do TLS. Um, okay, so at the internet layer, we add IP addresses for routing, and we handle packet fragmentation and reassembly. Um, so this is obviously since IP addresses are dynamically allocated by like your router. This is going to be through DHCP um, or Dynamic Host Configuration Protocol, which you can read a bit more about online. But basically, it's a way of whenever you enter the network, you can configure your IP. Yeah, cool. Then going through the link layer, which is the physical transmission layer. We frame the data for physical transmission, and we use the MAC addresses that we see from ARP, so from our address resolution protocol, um, to identify which device we need to send our information to. And then here we control media access and signal encoding. Now, media access and signal encoding is just basically everything related to what the hardware does. So this isn't really something that we need to know about for the exam. And then yeah, you operate ARP to resolve IP to MAC addresses, and then DHCP will dynamically assign IP and network information. So ARP, how does it work? So address resolution protocol, as we said, it helps you to like find and store the mappings of IP addresses to MAC addresses. Now, the reason we use this is because IP addresses are dynamically allocated and sometimes can even change. So we need to maintain the, the sort of physical identifier for our device. We need to know which device is actually using what IP, as the MAC address or the media access control address won't actually change. This is basically this MAC address is basically a physical address that's put into your device when it's being manufactured, and essentially this MAC address um, is basically used as a physical device identifier that's unique. So yeah, when a device needs to communicate with another device on the local network, it must translate the destination's IP to its corresponding MAC address to enable frame delivery. The ARP will store the IP to MAC addresses mappings, and the ARP process begins by firstly broadcasting a request containing the target IP. So basically, let's say it's like a router and like a new device is joining the network. The router would be like, yo, I can see that some device um, has an IP address, so that's allocated through DHCP, but we want to store it as well. So we'll be like, okay, who has this IP address? And then the device who just joined and got the IP will correspond to that, and basically we'll just say, okay, here's my MAC address. I am the one with the IP, which is then cached into the ARP table or ARP cache, address resolution protocol cache, which is where we store these IP to MAC mappings for things like future communications, reducing network traffic, and improving efficiency. Now, these aren't always going to be stored. It's a cache. So there will be like an age or like an expiry limit when we actually store these addresses. Um, so yeah. Now with ARP, it is vulnerable to ARP spoofing attacks. So basically what an ARP spoofing attack is when a malicious actor or a malicious attacker will send falsified ARP messages such that they can associate their MAC address with the IP of a legitimate like network resource. So basically it's like, let's say there's like two devices, my device and like another person's device, and the router is like, okay, um, whose IP is this? Obviously, let's say in this scenario, it's the other person's device that has the actual IP, but then I can say, oh, this is my IP, and and I'll just send my MAC address just so I can get it to forward all the information, um, or forward all the traffic that's meant for my IP address. Well, not my IP address, but forwarded. Essentially, the victim's traffic will be then forwarded to me. So this is basically like your MITM man in the middle attack. Um, so at that point, I can then intercept communication um, for the victim and sort of act as if I am like a router. I can act as if I'm sending data to the victim. Um, So yeah, you can see below how it works. So it starts with the top left, attack preparation. The attacker connects to the target network and identifies victims through passive monitoring. So they'll have things like Wireshark, where they will do like network packet analysis and stuff like that. Um, and they'll be able to like see how or like sort of how, yeah, how they can attack these victims. So then the attacker will send the spoofed ARP replies, associating their MAC with the gateway's IP. So basically, the gateway here is just the router or the traffic forwarder. So basically, they just say, okay, like they try to associate their MAC with that IP, that sort of says, okay, um, whose IP address is this? So they basically say to the device, the gateway that actually does the ARP protocol, they try to associate that MAC address with it. We then redirect traffic. So the victim's traffic routes through the attacker before reaching the intended destinations, and so the attacker can basically do whatever to it, and then send it to the victim. And in this way, the victim is susceptible to several different things. such as like social engineering, things like that. And also like key logging, well, not, sorry, not key logging, but like looking at what the victim is actually looking at. Yeah. Okay, so yeah, this is just a bit of information on MAC addresses. So, like I said before, MAC addresses serve as the physical address identifier. They are 48-bit addresses, and they're usually displayed as 6 pairs of hexadecimal digits. So if you've ever gone in your settings, on your phone or whatever, you've probably seen this sort of like hexadecimal address where there's like two sort of these like hexadecimal digits, um, and like they're separated by colons. That's most likely to be your MAC address that you might have seen. So while MAC addresses are designed to be globally unique and permanent, um, modern operating systems allow for software-based spoofing of these MAC addresses, which creates both legitimate use cases and security implications as well. Um, so, like, let's say, for example, like as an attacker, I can if I am able to in any way, shape, or form find out the MAC address of someone else's device, I can spoof it now, using software. So usually nowadays, like companies will use stuff like Wireshark, and like filter out MAC addresses and filter out um, like various different attacks that are related to ARP. You can do that through Wireshark filters. Um, and also just having a look at like packets, and seeing if there's any sort of like small change in these MAC addresses or whatever related to it. So yeah, okay, back to TCP UDP. So like we were saying before, TCP, Transmission Control Protocol, is a connection-oriented protocol, and it ensures that reliable data delivery happens with error checking and flow control. Error checking should be quite obvious to you guys. Flow control basically is a management technique for when we send data um, to a device. Obviously, we don't want to send too much data to the device, such that it's not able to read anything, which is where we have this flow control technique that will allow us to control how much data we're actually sending to this device at a given time, which makes it a bit more flexible and reliable. But yeah, TCP establishes the connection before transmitting data, which is the three-way handshake, and it guarantees packets arrive in order. And if there's any lost packets, then they are resent. And the person who receives the packets will be able to check this by computing things like the checksum, etc. Or there's usually some other information contained within headers. Now, coming back to UDP connection, it's a connectionless protocol that sends packets without establishing a connection, focusing on low latency over reliability. Like we said, an example of this is Discord. Um, UDP does not guarantee order delivery because obviously it has not got these header flags or anything like that. It has a smaller header, but it makes it faster, but it's less reliable. Now, um, if we go on to the next slide, I have a table of different sort of differences between TCP and UDP. So you can see like how TCP is more connection oriented, it's more reliable, and there's more ordering. It has flow control. Um, these brackets are basically just the um, sort of algorithms that we use for flow control. Um, Now, the UDP and TCP both have checksum, but they won't have things like your three-way handshake. It won't have sequence numbers for your packets, things like that. And obviously a lower header size. Um, but UDP has lower overhead, lower latency, and throughput can be higher, but obviously this means that it can overwhelm the network because there's no flow control. Um, And you can see that we have different ports for different protocols as well. but these ports are usually for different services. So, for example, we have HTTP has port 80, HTTPS has 443, things like that. Yeah, this is basically just the same thing. You can have a look at this in your own time. Cool. So, when we go on the internet, right, and we want to access a website, these websites are actually IP addresses. So, like, let's say google.com. This google.com is actually an IP address, but the google.com part is an alias. Um, it's what we call a domain name. So this domain name is much more easier for humans to actually use rather than IP addresses. So we have, well, we can't actually memorize like, I don't know, like 192.168. Something something, right? Like, it would be very hard for us to remember those. So we obviously use these domain names instead to actually um, go to websites. DNS. So yeah, essentially, point is, we have these IP addresses with numbers. We don't want to waste time remembering them, so we use words. We use these domain names, um, but obviously computers won't understand that. So there's this thing called domain name um, service sort of resolution. So we have this resolver or way of resolving these domain names in a way such that if we type in like our domain name, if we type in google.com, it'll actually go to the IP address, find the IP address, and return it to us. And then we will type, and essentially in the background, we connect to the IP address, and we are able to get access to the specific service. So yeah, essentially it's the internet's phone book translating human readable domain names into machine usable IP addresses through a distributed hierarchical database. And you can see how this database works as I'll start explaining. So first of all, in order to actually find out what the hell our IP address is for our domain name, we do this. We first look in our local DNS cache. It's basically just a cache of domain name to IP mappings. Um, this is for things that are like frequently used, so like google.com would probably be in there. And when you download a browser, there's going to be a lot of them that are already in there as well, which are usually going to be more so your popular websites. So like if you ever see like when you try to search for something and like you can see like your previous things that you've gone on quite frequently on there, that's your DNS cache. Um, okay, then if our IP address isn't for the domain name that we're looking at, if it's not within the local DNS cache, we then send a query to a resolver. Now, this is usually provided by your ISP or your internet service provider, and it will basically take responsibility for finding the answer. Um, so essentially, this ISP will basically do all the searches and will bring you back the IP address. Now, essentially, the way the resolver does it is essentially it will look at the root name server. So root name basically means things like when you have .com or .net or .app, right? Those kind of things are your root name. And so we first the ISP resolver will first ask the root name server for the top level domain name server responsible for those domains. Um, so when we go to the root name server and we find the top level domain server that is responsible for the specific .com or .org or .net, we'll then query that server, we'll query that top level domain server, um, and then that server will then query the authoritative name server, which is actually responsible for the specific domain. So like example.com. We then return the actual IP address from that name server, and basically it just goes back through that chain of sort of queries that happened, which goes back to resolver, and then resolver provided by the ISP will send it back to us, and then it's up to us if we want to cache it or not. This is usually dependent on the browser or your OS. Okay, So yeah, like before, we were talking about sort of Wireshark and things like security on the network when we have internets and sockets. Um, also, oh, I actually forgot to include sockets in this. But sockets are quite simple, so I can cover this just quickly. So sockets, basically, sockets are the port and IP combinations for things like TCP. So like when we were talking about the ports and IP addresses before, um, a combination of those is basically what will allow you to actually send and receive stuff from your various different things, right? From like Google.com or whatever, right? Through various for various different services as well. So yeah, that's basically what a socket is. Um, Anyways, back to network security. And how does a socket differ from a WebSocket? Uh, to be honest, I have no clue. Sorry. Um, yeah, I actually haven't dealt with WebSockets before. I know they exist. Um, I mean, I guess one. I think what WebSockets are. I think it's just a service. So I think a WebSocket, when we refer to like actual programming, I think this is what I'd assume at least. I probably might be wrong, so obviously take this with a pinch of salt. But when you actually have WebSocket like addresses, usually it's like WSS colon slash slash, right? So usually it's probably to do with the actual service. So WebSocket is a service on a socket that is used for some sort of communication. That's what I can think. Let's see what Shay has put from ChatGPT. Yeah. So yeah, no, WebSocket is a protocol built. So it's a service, yeah. So like TCP, WebSocket, well, not even like TCP, it is basically a protocol on top of TCP. So yeah, it's basically a a sort of thing where we use it's a type of service that we use on the socket, which will require a port number and an IP. So WebSocket is just one of those services. So yeah, thanks, Shay. Okay, cool. Sockets can be either TCP or UDP. Yeah, exactly. Sockets can be whatever service like you use. Um, as long as they have a port and an IP address, they can have whatever protocol. Yeah. So network security best practices. Now, like we say, when we have these internet stuff, when we have this socket stuff, obviously, um, there's a lot of different ways in which you can attack these. So we need to ensure that we're not being attacked. Um, One thing to at least note before we cover everything is that any security model assumes that the attacker can control a network. Essentially, the only good protection against attacker is strong encryption. And if strong encryption is broken, then there isn't anything else we can do. So essentially, unencrypted data is compromised on the network. That's what we assume. So, um, yeah, firstly, Wireshark. A lot of companies will use Wireshark to detect and analyze these weird network packets in real time, i.e., like abnormal traffic or potential attacks. We can filter out ARP spoofing. There's actually specific commands that you can use with Wireshark to do this. And you can monitor ARP packet patterns or inconsistencies. Now, in order to prevent ARP spoofing specifically, you can use static ARP and not dynamic entries, as dynamic entries um, can be spoofed, whereas static ARPs cannot. So on your critical devices, on the ones that you want to protect the most, you want to use static ARP, um, and also enable dynamic ARP inspection on spotted switches. So basically, like just toggle on those filters to sort of detect these weird ARP spoofing things. Um, but yeah, essentially, when an attacker successfully spoofs ARP, they can essentially own the network. so they intercept or alter traffic at their will, i.e. MITM, things like that. MITM standing for man in the middle. But yeah, hopefully that session has helped you guys. If there is any questions, please do let me know. And yeah, thank you guys for watching the video. Make sure to like, subscribe, comment down below what you thought, and click the notification bell for the next video. All right, see ya.